Let's do a problem on exponential growth. And if you think about it, what we're going to do here with bacteria, it's no different than what we did with compound interest when we learned about interest and the number e. Because if you think about it, well, I'll draw the analogy as we do this problem. But anyway, this is a compound growth problem or an exponential growth problem, and it says a bacteria culture initially contains 100 cells and grows at a rate proportional to its size. After an hour, the population has increased to 420. So it first says, find an expression for the number of bacteria after t hours. So in general, anything that when you're dealing with exponential growth or exponential decay or continuously compounding growth or continuously compounding decay, although you'll very seldom hear that term, the amount of whatever you have as a function of time will be in this type of equation. I'll say bacteria is a function of time, so I'll say b of t, and I'll do it here. So b of, well, let me do it here. B of t. Bacteria as a function of time is going to be equal to the initial bacteria, or the initial of whatever we have. If we're doing compound interest, it's the amount we start with, e to the kt, where k is kind of our compounding rate. And so in general, if you have this I naught, your initial, the initial amount you have, and that makes sense, right? Because if t equals 0, this whole expression is 1. So b of 0 should just be I naught. So if you know what you start with, and then you have another point, you can solve for k, and then you have an expression. You have what the first thing they want. Find an expression for the number of bacteria after t hours. So my question to you is, first of all, what is I sub 0? What is your initial number of bacterial cells? Well, they tell us. They tell us right here. The bacteria culture initially contains 100 cells. 100 cells. So we know that b of 0, right, when time equals 0 or 0 hours, that is equal to 100, where the unit is cells, right? And so if we substitute here t equals 0, this is 1, so we know that I naught is equal to 100. Let me do that actually. So b of 0 is also equal, if we look at there, I naught times e to the what? K times 0 times e to the 0 is equal to I naught. So this tells us that the bacteria at time 0 is 100, and then when we substitute here, it said the bacteria at time 0 is equal to I naught, so I naught must be equal to 100. Okay, so we're making some progress. So we know that the bacteria, as a function of time, is equal to I naught 100 times e to the kt. Now if we just knew k, then we would have done this part A, find an expression for the number of bacteria after t hours. Well, how can we figure out k? Well, they give us another data point. After an hour, the population has increased to 420. So that tells us, so let me, my phone is ringing. Who is it? Oh, it's free satellite long distance. I don't want to, oh boy, that phone is so far away. Let me turn it off. Oh, so annoying. This is not Dish Networks. Anyway, so what was I doing? Oh, so this tells us after an hour, the population has increased to 420. So that tells us that b of 1, right? After 1 hour, the population has increased to 420. So b of 1 is equal to 420, which is also equal to, what? If we put 1 here, that is equal to 100 e to the kt. Well, what's t at b of 1? T is 1, so e to the k. Right? So 420 is equal to 100 e to the k. And now we can solve for k, and let's see what we get. So we'll divide both sides by 100. You get 4.2. Let me put e to the k on this side. E to the k is equal to 4.2. Or, to solve for k, we take the natural log of both sides, and we get k is equal to the natural log of 4.2, which is going to be some bizarre number, and we'll figure that out later with a calculator. So there, we figured out, using the initial condition here, we figured out I naught, and then using this extra data point, we solved for k, and we got k is equal to the ln of the natural log of 4.2. So what does that leave us? So now we know the equation. We know k and we know I naught, so we know that the equation is, so part A, the equation is b of t, bacteria as a function of time, is equal to the initial number of bacteria, 100 cells, e to the kt, and k is ln of 4.2, that says 4.2, and all of that times t. So that's our function. I know you can't read that, but we'll use it again, so it should make a little sense. So then they say, find, this is part B, find the number of bacteria after 3 hours. So that's pretty straightforward. We have our function now that at any time t we can tell you how many bacteria there are. So let's figure out the number of bacteria after 3 hours. So b of 3 is equal to 100 times e to the ln 4.2 times 3. And that number we could calculate if you have a calculator, e to the ln of, well, let's see. That's essentially, well, what's this going to be? This is the same thing. We can actually figure this out analytically. That equals 100 e to the natural log of 4.2. If you have two things in an exponent multiplied, that's the same thing as taking that and then raising it to the third power, right? If we were simplifying, we'd say, oh, that's the same thing as just multiplying that times this. But what's e to the ln of 4.2? What's 4.2, right? Because natural log says, well, what exponent do I have to raise e to get 4.2? So if I raise e to that exponent, I get 4.2. So that equals, I didn't even have to use a calculator, look at that, 4.2 to the third power. And I don't know what that is. That's going to be probably 70 something. So we'll do that later. But that's part B. That's just plugging into your calculator. That's part B. Now what are they asking? Find the rate of growth after 3 hours. The rate of growth after 3 hours. Let me do that in a special color. So what are they asking us for? Well, they're essentially asking us what is the slope of this function after 3 hours, of this function after 3 hours. Or another way you could view it is, what is the derivative at time is equal to 3? Let's do that. Let me erase all this other stuff I have. I think we can erase all of this because we've written down our equation here. We can erase that. Actually, we could even erase all of this because we just answered that. That's just plugging into a calculator at this point. I just want to keep our equation, our original equation. So let's do part C. Part C, find the rate of growth after 3 hours. So we just have to take the derivative of the bacteria function with respect to time. So let's do that. So b prime of t, it equals what? So what's the derivative of, let's just do the chain rule. What's the derivative of, so we can just have 100 constant out there, times the derivative of this inside function. Well, that's just a constant times t, so it's just a constant. So times ln of 4.2 times the derivative of e to the whole thing. Well, the derivative of e to the x is e to the x. So just the chain rule tells us it's just the derivative of this whole expression. So times e to the ln 4.2 t. So that's the derivative at any time t. And then they want to know what the rate of growth is after 3 hours. So b prime of 3 is equal to 100 ln 4.2. All of that times, well, e to the, as we just did this in part B, e to the ln 4.2 times 3, that's the same thing as, because this expression right here is just 4.2. This is times 4.2 to the third. That's just a little bit of logarithm math we did here. And it's the same exact logic. And all I did is I substituted 3 here and simplified. Hopefully that makes sense to you. If it doesn't, you might want to use your calculator. But it's actually a pretty important thing to know, that e to the ln of x is just equal to x. Right? Because ln of x is essentially saying, what exponent do I have to raise e to get x? So if I raise e to that exponent, I get x. So that's all I'm saying here. That this right here is is the same thing as e to the ln 4.2 to the t, right? Because if you were to simplify, you just take this exponent, multiply this, and you get this. And so this is just 4.2 to the t, right? And actually, I should have written our original equation as that. I could rewrite our original bacterial function equation as 100 times, using that same thing, times 4.2 to the t power. Actually, that is a simpler bacterial equation than this one. And so that would be even a better answer for part A. And that makes part B even easier to solve. And then part C, well, part C is actually, it was easier to keep it in this form because taking a derivative of E is easier than taking a derivative of another base. And actually, this is, we would probably want to convert backwards, so it's good we left it in that form because it made the derivative all that easier. But we could rewrite the derivative as well. We could rewrite this as b prime of t is equal to 100 ln 4.2, all of that times 4.2 to the t, right? I just took this, sorry, no, I took this and I replaced it with this. Anyway, I got a little bit messier than I wanted to. But then their final question is, when will the population reach 10,000? So let me erase what we did in part C. When will the population reach 10,000? Let me write what we've already done a little bit neater. We knew that part A, b of t is equal to 100 e to the natural log of 4.2 t. And I said, well, you know, that's the same thing. It's 100 times 4.2 to the t power. And they say, when will the population reach 10,000? So they're essentially saying, at what time t is b of t equal to 10,000? So we could just say 10,000 is equal to this. 100. And actually, I'm going to use this one because I'm going to take the natural log of both sides and it just makes things simpler. 100 e to the ln 4.2 t. See, we can divide both sides by 100 and you get 100 is equal to e to the ln 4.2 t. And now we can take the natural logs of both sides of this equation, right? So that we get what? We get, let me draw a divide, well, I'll do it in a different color. We get, taking the natural log of both sides of this, the natural log of 100 is equal to, well, if you take the natural log of e to something, you're just left with the something. And you might want to review all the logarithms if you found that a little confusing. But that, if you take the natural log of this side, you're just left with the exponent. So that equals ln of 4.2 t. And if you want to solve for t, you just divide both sides by ln of 4.2. And you get t is equal to ln of 100 divided by the natural log of 4.2. And that'll be an hour. So how many hours does it take? You just plug this in your calculator and you will get a number for the number of hours. Hopefully you didn't find that too confusing. And actually, since just to hit another point home, we could have used this equation. I mean, it's the same thing, right? And what we would have had? We would have had 100 times 4.2 to the t power is equal to 10,000. Divide both sides by 100 and you get 4.2 to the t is equal to 100. And so to solve this, so you're essentially saying log base, you would essentially want to take log base 4.2 of both sides of this. So you would say t is equal to log base 4.2 of 100. And I went over this in the exponent in the logarithm properties video, but it's a pretty useful thing to know in general. How do you figure out, you know, your calculator has two bases. It has log base 10 and it has log base e, which is the natural log. how do you figure out log base of another number of 100? Well, the simple answer is you could take natural log of this and divide it by the natural log of this. You could also take log base 10 of this and divide it by log 10 base of this. Log base 10 of this. Anyway, hopefully I didn't further confuse you, and I will do, this was actually exponential growth, and you could replace these words. You could say, you know, instead of bacteria culture, you could say a bank account initially contains $100 and grows at a rate proportional to its size, which would mean compound interest. And then you could say, after an hour, the population has increased to whatever, $4.20. And then find the expression for the number. So essentially you'd be trying to figure out the compound interest rate and all of that. But this is the exact same phenomenon, that the larger you grow, you're going to grow by an absolute value more than that. Anyway, I'll do more of these problems because they can be a little confusing, and I'll do one on exponential decay as well. See you soon.